My advice is to start with juggling scarves. If you juggle these 3 in 2 hands or 2 in 1 hand, they float. There's a tremendous amount of air resistance. They don't move very fast, and you have a lot of time to be able to figure out where your hand has to be next. Juggling balls is a little bit more complicated, and the reason is you don't have as much time. If I try to juggle 2 balls in 1 hand, the balls go up, they come back down, and it's quick. I have to quickly figure out where my hand has to be. How can I buy myself more time? Well, if I do it small like this, very fast up and down. If I throw them up higher, I get more time. And so if you're learning to juggle, you want to do it in a room with a high ceiling, because you can throw them up farther, they're up in the air longer. Let's look at a problem that deals with this very question. Here's the question. A juggler is performing in a room with a high ceiling, tossing balls from hand to hand in high arcs. If the ceiling is 2.1 meters above where he releases the balls, what is the maximum time between tossing a ball up and catching it again? Now there's one crucial piece of data in this problem, and it's this. The ceiling is 2.1 meters above where the ball is released. So the ball is going to go up in the air 2.1 meters, and then it's going to come back down again. The maximum time is going to be if the ball goes all the way to the ceiling. Let's think about how to solve that problem. We're going to start by doing a visual overview of the problem. Now let's look at the motion. The motion of the ball does something like this. The ball starts at a certain height, and then it goes up, turns around, comes back down again, and then finishes at the same height as where it started. And we know that this distance between where the ball starts and where the ball finishes, that distance is 2.1 meters. Now, I want to look at a graph of the motion next, because that's going to be really instructive for us. So we want to look at a graph of the vertical velocity as a function of time. Let's sketch axes. Here's Vy on the vertical axis, t on the horizontal axis. And what will the graph of the velocity as a function of time look like? We'll give you some choices. Once the ball's left the juggler's hand, it's in the air. And the only thing that's working is gravity. This is a free fall problem. So what that means is the acceleration is constant and it's directed down. So the velocity starts positive, the ball is moving upward, but then it steadily decreases. And so we end up with a straight line that looks like this. And there's a couple of special points on the motion. There's a point right here, which is where the ball is thrown. There's a point right here where the ball is caught. That's the end of the problem. And there's this point right here. And we want you to think, physically, what is happening at this point? What is the ball doing at this instant on the curve? Think about it. We'll give you some choices. Let's look at the motion again. We're going to sketch the graph. We're going to have the vertical axis is Vy, that's the vertical velocity. The horizontal axis is t, the time. And the velocity starts out positive, goes to 0, and then goes negative. The point right here in the center, where the velocity is 0, that corresponds to the point when the ball is at its highest point. Okay, so that's going to be an important point for us. Let's think about the different segments of the motion. This first phase, right here, we start out with a positive velocity that goes to 0. That's the ball on the way up. Second phase of the motion is this one right here. The ball starts out with 0 velocity and goes negative. That's the ball on the way down. Turns out it's this phase of the motion that we want to solve for. This phase right here, where the ball is at 0 velocity, velocity is going negative and it's on its way back down. And if we solve for this half of the motion, the total motion from the ball going up, turning around and coming back down again is just double that time. So let's take a look at that problem. And now, and only now, is the time to think about an equation. And the equation is going to be the equation for motion with constant acceleration. Since it's vertical motion, we're going to use the variable y. And our basic relationship looks like this. The final position is equal to the initial position plus the initial velocity times the time interval plus 1/2 times the acceleration times the time interval squared. That's our basic relationship for motion with constant acceleration. And we know it's constant acceleration because we know that the ball is in free fall. And free fall is an example of constant acceleration. Now, if we look at this equation, there's a couple of values which we need to put in. We need to put in a value for the initial position, the final position, the initial velocity, and the acceleration in the y direction. Those are the four values that we need to put in. Let's think about them. The initial velocity, that's just 0, because we know that the ball starts at its highest point, the velocity is 0. So this term goes out of the equation. We can get rid of that. The y acceleration, we know what that is. It's free fall. And so the value of the acceleration is just minus 9.8 meters per second squared. So we know that. But how about these 2 points right here? We need to know what are the values of the final position and the initial position. What should we use for those values? We'll give you some choices. The initial position of the ball is when it's at its highest point, because we're doing the phase of the motion when the ball is at its highest point and comes back down again. And if we're throwing the ball as high as possible, the initial position is 2.1 meters above the ground. The final position is back in the juggler's hand. Let's take that as our 0. So it starts out at a height of 2.1 meters, finishes at a height of 0 meters. And so it's dropped by 2.1 meters. That's just right. That's just right. We have all the variables that we need in this equation. And so at this point, we're ready to substitute numbers and do a calculation for the time. And let's do that. We'll rewrite the equation and put in those values. The final position, 0 meters, is equal to the initial position, 2.1 meters, plus, and then the velocity term went away. So we have the acceleration term plus the acceleration, which is minus 9.8 meters per second squared, times the time interval squared. And what we're looking for in this equation is the time interval, delta t. That's what we're solving for. And now the problem's reduced to algebra, and if we solve for this time interval, if we go ahead, put numbers in a calculator, and solve, what we get is the time interval, delta t, 0.65 seconds. But that's not the time we're looking for. We're looking for the time for the ball to go all the way up and come back down again. And remember how we drew the graph for the motion. If we look at the y velocity as a function of time, there's two phases. There's the ball going up, and then there's the phase of the ball coming back down again. And the time interval between when the ball's at its highest point, when the ball comes back down to the ground again, that time is 0.65 seconds. So the total time is double that. The total time, 1.3 seconds. That's how much time the ball's in the air. That's how much time the juggler has to react in this particular room. That's the answer to our question, 1.3 seconds. We found a time of 1.3 seconds between when a ball is released and when it's caught again. That sounds about right. If you think about a juggler throwing a ball high up in the air, a time of about a little bit more than a second sounds about right. If we found 100 seconds, that would be kind of a surprise. That would be far too long. You don't expect to throw a ball up in the air and be able to have a conversation before it comes back down again. 100th of a second doesn't sound about right. 1 second seems on about the right order. And in fact, we can test our result. This room, the ceiling's about 2.1 meters above where I'm going to release the ball. If I throw it up in the air, let it go up, come back down again, it's a bit more than a second, just what we calculated. Not a surprise. Physics is about the world around us.